When you guys take your notes, I want you to, okay, you see how I color code a lot of my stuff, right? I color code a lot of my notes because I know that certain things will trigger a response in your brain. So for instance, last night or yesterday, we were talking about reactants, right? Matter of fact, let me see if here's what I want to provide clarity with. So those of you all that are new, welcome back. Welcome to the live. My name is Professor TK the Chemist. I do teach chemistry for real, not for play, and I help bring clarity to students that need help to give them confidence in it. So we've been talking about kinetics and rate laws for almost 2 weeks now. So next week, we're going to get into the ICE tables, okay? And we're going to talk about that so that okay, welcome, Trezor. All right, so we're going to actually get into that tonight or today now. And if you all want to come back for more, I go live also at 8:30 p.m. All right. So one of the things I wanted to share with you is that when it comes to rate laws, you have to look at the reaction that you have and look at the experiment. And then in order to determine the order, that's going to allow you to do so based on the information provided. So in this particular example right here, and I'm going to actually dial between these set of notes and the other set to explain the zero order and all of that other good stuff. Okay, so we're going to actually go into both of them right now. So in this first example here, you have A plus B, right? A plus B. We don't worry about C. We don't even worry about the product side. It's only based on the reactant side. Whenever you're looking for A, trying to determine the order for A, you're going to make sure that B holds tight. You want to make sure that B remains constant. So that means if I'm comparing experiment 1 and 2, because B remained constant, okay, did not move or anything, you're going to look at your data. Right here, I do notice that the reactants doubled. So my rate here quadrupled, okay? So I have to determine my M. So some of you all may be familiar with the M as it relates to this formula here. Rates, whenever you have two reactants, okay, it could be A to the M times B to the N, whoops. But it depends on whether or not one of them goes to 0. All right. This is your standard formula, but it could change. It could change. You could also have rate equals K and then A just like that to the M, where it could be square. So, and I'm going to get to that in a moment, all right? So in this case right here, based on our data, we notice that A doubled, the rate quadrupled, so we have to determine by what factor or what exponent rather should my box contain, because it started off with 2, so what factor do I need to have up above to say that it's equal to 4? Well, it's the number 2. So that's the second order. Okay, with respect to A. So this is A's data. Now, to find B, okay, to find B, we need to hold A constant. So this is A now, holding constant. So experiment 1 and 3 holds constant. So therefore, I need to look at 1 and 3 for B. And I noticed here that it doubled, okay, for A and B. I'm sorry, it doubled for experiment 1 and 3 for B. Therefore, I look over here now for my rate, but that remained the same. And since the rate remained the same, although my reactant of B doubled, what is that order? So let me show you this here. So if it went to 2, but over here it remained the same, by what factor do I need to put here in the box to indicate that it's 1? And this is actually 0, okay, 0 order. Now, I need to provide clarity on what I had mentioned last night, because in this case right here, guys, if you all use your calculator and you know that 2 to the 0 power equals 1. Oh, good. Hey, thank you, Nisha, baby. Thank you so much for coming in with that positive word. Thank you. You stopped by to tell me you got a 92 last semester because of my YouTube and TikTok. Honey, I thank you for coming in telling me that good news. Thank you, thank you, thank you. Yes, I appreciate that. So when you all look at this one right here, I also mentioned, because that's 0 order, we do not include B, okay? We do not include B. So therefore, when we rewrite this, okay, the overall order here is 2, okay? Oh, yeah, this is still part of kinetics. Yes, this is still the chapter on kinetics. Yes. Now, what I need to actually tell you though is that when you look at the units will tell you the story in terms of what you're working with. You're welcome. In terms of what you're working with. So if you noticed here that the overall order, okay, is M plus N, which equals to 2, then that means you will not include B in your final formula. So because B is equal to 0, okay, order B is equal to 0, that means my formula overall will be K times A to the second. And that tells you second order also. The overall order is 2. It tells you this is second order. All right. Now, I wanted to also dispel the myth about the 1, because sometimes the 1, in chemistry, we say the 1 is understood. We say that in math, but it's also applicable to chemistry. Like when you're balancing equations, you don't have to put a 1 in front of certain elements or compounds because they're understood. Well, let me give you an example. Let's see here. Let me find it right here. Let me see. Let me erase all this so you all don't see that too. Okay, because I'm gonna explain that one as well. Okay. When you think about having a 1, the 1 tells you, excuse me, y'all, the 1 tells you that it's understood to be there. So we do not have to incorporate that in our problem. Okay. We do not have to incorporate that in our problem. So therefore, when we are doing these problems, I want you all to understand that chemistry is just like math, okay? So let me go ahead and break this one down. This next one, you have 2x plus y equals z. We don't have to worry about the z part. We're just going to ignore that for right now. So right here, what is the order in x? Okay, remember how I said you're going to hold y constant so that you can focus on x, okay? So when you're focusing on x, you're going to make sure that y doesn't change. So because the first 2 experiments represented that, in this case right here, experiment 1 and 2 shows that x doubled. Well, this also shows me over here that my rate for experiment 1 and 2 quadrupled. So you already know that 2 raised to the power of 2 gives me second order for x. Now, as it relates to y, okay, as it relates to y now, I'm going to change up the colors so y'all can think a different color change. I'm going to hold x constant. I'm going to hold x constant now. Okay, so that means experiments 2 and 3 are held constant. So therefore, I now need to look at y's reactant. In this case, these 2 doubled. Okay, and what did these 2 also do? They also doubled. So if 2 equals 2, then that means this is first order. Hey, Liv, or Liz, or yeah, Liv, alive. Thank you. Because that's first order for y, okay? That's first order as it relates to y, then the 1 is understood, okay? The 1 is understood, so we do not include that. So when we write out our rate law, okay, we would say rate equals A to the second and then B, just like that, okay? But now let me explain to you that even though we don't put the 1 there, what would be the overall order? So let me go ahead and dive over here to explain what that represents, okay? So here are my notes. All right. When you have, like I said before, zero reactant, okay, a zero order is typically when you have just one reactant anyway, okay? But also, if you have two reactants, one of them could actually be zero order. So you're just going to write down the element or the reactant, that remains. So what does B to the 0 actually means? Okay. Here's something that you all can think about. Changing B does nothing. It doesn't influence the rate and is not involved in the slow step. And we talked about rate mechanisms yesterday when we did several examples about that. Okay. What it does tell you is that it's probably in the fast step or not in the rate determining step at all. So when you actually write out your rate response, you may not even have it at all. Now, when we mentioned first order, okay, and how I said the 1 is understood, check this part out right here, okay? You see how A doesn't have an exponent, nor does B, okay? This illustrates that rate depends directly on A and B, and they're both involved in the slow step. So if you double the reactant of A, what this means is that your rate will also double. If you double your reactant of B, your rate also doubles. And if you double both A and B in your set of data points, then your rate increases 4 times the amount. So here's an overall response that you all need to know right here, okay, in terms of those exponents, okay, in terms of your exponents. If you have a 0 order, the exponent is 0, yes, but you do not let that appear in your rate law, okay? If you doubled the reactant of B, then the rate has no change. And again, you can see the same thing over here, all right? You can see the same thing over here. Now, I do want to show you an example so that you all can kind of, again, digest this information. And then I'm going to actually go to the question that a student emailed me so that I can explain to you, another method of practice problems. A lot of students say, well, no, like the way you show it looks so easy. The questions look different when we take the test. They're all the same. And I got a worksheet to prove it because she actually sent this to me, and I'm going to show it to y'all in a second. Take a look at this first case scenario. 0 order for B. Let's look at it. Here's how you could think of it. When you have first order in A and 0 order in B, this means that when you look at experiment 1 and 2, okay, right here, 1 and 2, okay, notice that your B doubled, but your rate remained the same, okay? Your B doubled, your rate remained the same, therefore, with respect to B, B is 0 order. All right, remember, keep A constant, look at the data for B, and look at the rate for B. It doubled, it remained the same, so therefore that's 0 order as it relates to B. Now, if I look at A, I have to keep A constant. So let's look at keeping experiment 1 and 3 the same. Well, 1 and 3 here shows that they doubled. Okay, doubled. Over here for 1 and 3, it also doubled. Okay? It also doubled. So therefore, that would be first order. Okay? That would be first order. But when you write out your rate law, you don't put the 1 because the 1 is understood and the 0 order is not included in the final formula. And this is why your final rate law is that right there, because 0 is not included. So the overall order would be 2, and your units would reflect that. Okay? Your units would reflect that. Here's another example right here. And I'm going to upload this video specifically on this section here alone, talking about the 0 and 1 exponents when you write them, because a lot of students get that part wrong on their test. Okay, same thing here. Let's say that you have first order for both A and B. So if I'm looking at, let's say, experiment 1 and 2, okay, for B, all right, again, for B, I'm keeping A constant, but I have to look at the data for 1 and 2, okay? They both doubled, so that's first order. They both doubled. However, if I were looking at A, I'm going to keep B constant right here, okay? I can do experiment 1 and 3, or I can do experiment 2 and 4. It doesn't matter, okay? It doesn't matter. So I'm going to do experiment 1 and 3 so you all can see this part right here. Therefore, 1 and 3 here doubled. You see that? From A, right there, it doubled. So right here, it also doubled. So that's why A is first order. But let me show you if I put it, if I did experiment, let me erase this too so you all don't get confused. Let's say that I was looking at, as it relates to still letter A, okay? Let's say that I wanted to look at experiment 2 and 4, okay? Keeping B constant, then these two right here doubled, and this also doubled, and it's still first order, okay? It's still first order. So therefore, you do not need to incorporate those exponents in terms of the 1 because the 1 is understood. All right, now, the question that the other student had for me. Let's see. Let me pull it up because I took a screenshot. Let me make sure. Okay, so are there any questions though? And you do know the overall order would be 2, okay? The overall order would be 2. Make sure you all understand that. The overall order would be 2. So right here, this is your problem, okay? This is the problem. And it says you have a reaction, okay? That they're giving you a lot of information in here. You've got, first of all, you remember how I said, if I give you all an actual problem with like real numbers or real reactants, could you do the same thing? And the answer is yes, okay? So for a question like this, right here, they're asking you to determine the rate law, okay? So what we're going to do right here, we're going to break this down in the simplest form. But first up, let's identify all the information that's given. You have this reaction right here, right? And remember, I said we don't care about the product side. But here's something that you do know. If you just have one reactant, then what is the rate law going to be? Okay? And you can get the order from knowing that part. So because you just have one reactant, the rate is going to, going to be K times NO2, okay? And in this case right here, something else that you want to be mindful of, look at what they provided you with here as well. They said that this is a rate constant, right? It has a rate constant of 84 per molarity per seconds. When you see these two things here, okay, when you see these two things right here, something that you all can do is let the units guide you into what you're working with. Remember, I showed you all this yesterday. The units will guide you into what you're working with. Right here, I mentioned this. Let me see if I can go up here and pull it down. Right here. I'm going to zoom in. See this? Per molarity, per seconds. That illustrates a second order reaction. So even though you'll look at your problem and say, okay, let's see what I got here, also know that your rate constant units tells you the story. And in this case right here, you're going to say second order, all right? Because of these units right here. All right. Excuse me. Now, in part B, because they're telling you the half-life of, they want you to do the half-life of the reaction, go back to your formulas and know, well, what is the formula for half-life for a second order reaction? In this case, we're going to be working with 1 over K times the initial concentration. They have to give you the units because the units will tell you the story. So we cannot leave this problem hanging without units, okay? Because the units are going to tell the story. So again, and if you just go back to this part right here, because we're working with second order, this is the formula that you guys are going to use for your half-life. Whenever they say how long something's going to be, based on a reaction, you're going to use the half-life part of your formulas, okay? You're going to use a half-life formula for that. So you're welcome. So right here, we're going to plug in our numbers. 1 over your rate constant was at 84 per molarity per seconds times your initial concentration. And the initial concentration was this number right here, 0.250. So I'm going to put that number down here, 0.250 molarity. And remember, your M's are going to cancel out. And because you're looking for time, it's your seconds that's going to count. All right? Oops. It's your seconds that are going to count. So therefore, when I plug this in, I'm just going to say 1 divided by, and then whatever, 84. Let me plug this into the calculator. Let me pull up the calculator now. So we're going to say 84 times 0.250, and we get 21. So you got to say 1 over 21. So your half-life is equal to 1 over 21. So let's divide that out. Okay, 1 divided by 21, and we get 0.0476, these long numbers, but we're just going to round it off to 0.0476. 0.0476 seconds. Okay, so that would be your answer right there. That's for letter B. Now, for letter C, when they ask you, all right, well, the amount of reactant remaining after 3 half-lives is what? Well, the easiest thing to do is to take the answer you got from part B and just multiply it times 3. So 3 times 0.0476 will tell you what your answer is equal to. So let's pull up our calculator again. Okay. And then multiply that. So 0.0476, multiply that times 3, and we get 0.428, 0.1428 seconds. Okay. That's what has happened. Now, a lot of times when you're doing these type of problems, you'll notice that there are parts to them. If you do not do the right thing, and we're not done with this yet though, okay? Because we still have more to go with this particular part of the problem. If you do not plug it in properly, you'll fall by the wayside, okay? Meaning if you don't have B answer correct, you're not going to get C correct. Now, this question says the amount of reactant remaining after 3 half-lives. So first thing you got to do is calculate the number of half-lives that has passed. Then you've got to plug it back into the second order integrated law, okay? So this problem here would have a multiple component to it. But you have to do this part right here first in order to do this second step over here. Okay, so the second step is to apply the second order formula of the integrated rate law. Okay, so that's 1 over A equals, and again, if you forgot the formula, let me show it to you, because again, as a visual student, you got to still see it. It's 1 over A equals 1 over the initial concentration plus K times T. There are only 2 on here that deals with subtraction, but there is only one that's positive, and that's the second order one. Okay? So 1 over your initial concentration plus K times T. Now, you're going to go back up to your data in case you forgot what the initial concentration was, which was 0.250. Okay. So you're just going to plug that number in right here. So 1 over A equals 1 divided by, and again, they gave you 0.250. And that's molarity. Plus, they also gave you your rate constant, okay? And again, in case you didn't see that number, let me go back up here so you can see it. 84 molarity per molarity per second. So I'm going to put that number right here, 84 per molarity per second times your time. Now, again, your time comes from this part right here, that step. 0.1428 seconds. And guess what's going to cancel out? Your seconds. Because you need your molarity. Okay? You need your molarity. So now, in this part right here, okay, let me scoot this over. Whoops, nope. There we go. Well, no, hold on, y'all. Trying to get it down here. That was D. Let me put D right there. That way y'all know this is a 4-part problem. Okay, there we go. So you're going to say 1 over the natural log of A equals, now go ahead and divide that 1 divided by 0.250. And we get 4, okay? 4 molarity plus, we got to multiply those two numbers right there. So 84 times 0.1428, and we get 11.99. Let's round that off to 12, just for the sake of working with these numbers right here. And that's molarity. Okay? So what you're going to do is say 1 over A equals, what's 4 plus 12? 16. But now remember, in order to get A, this is some quick math right here. You're going to swap these two. You're going to swap them, meaning you're going to rewrite this over here as A, meaning the reactant of A is equal to 1 divided by 16. Okay? And ironically, there are 16 people in the lab. So y'all hit that them hearts up. 16 people, 1 divided by 16. That gives us 0.0625 as our final answer for this problem, okay? 0.0625 molarity, okay? Thank you for the rose, Axon 21. Thank you. Okay, good question. How can you just change that per M to M? Hey, Ash, very good question. Okay, this is what's happening. Let me break it down for you, okay? Whenever you have 1 over M, and then this up here was the M to the -1 is the same thing as saying 1 over M. And because I already knew that that was going to be on the bottom over here, when I put those two together, I automatically knew to take that to the top. So when it's on the bottom, and then you had to do a remix of this section right here, the unit became molarity overall. Also, that's a good question too. Also, one thing you have to remember is that when it comes to the reactant, your unit will always be molarity anyway. Okay? So that's just like saying, if I want to know how much, like if I say, how much do you weigh? You don't say you weigh 150 per pound. You say I weigh 150 pounds. Once you go through all the math, your final unit has to be in molarity and not per molarity. That was a good question. That was a good question. Now, in this last part for letter D, it says, well, it's not really the last part, but it's the next part, the next part right here. It says, the amount of time necessary to consume 99.9% of the reactant. What is the amount of time necessary to consume 99.9% of the reactant? Well, here's the interpretation by that. If you know that you've consumed 99.9%, well, what remains? 0.1% remains. So all you're going to do is you're going to take the concentration that you had from up above, not this one that we just found, right? You're going to take your remaining concentration, okay? And you're going to end up multiplying them. So let's go back up here. Okay? So it's like you have to go back and re-evaluate what you had, all right? So you got to take what you had initially, okay? That was what you had initially. But remember, you have 0.1% of that that's left over. So you're going to take 0.1% times that, all right? That tells you what's left over. So right here, you're going to say, you're going to have to change the 0.1% to a decimal. Unless you know how to, use a percent key, you're just dividing that by 100. But 100 divided by the 0.1% gives you 0.001. You're going to multiply that times 0.250. And that tells you 0.000 25. That's what's remaining. Okay, good, 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 good. Thank you, Yogasen. Appreciate you. Thank you for your gifts. Okay. So now we're still not done because they're asking you for the time. It says the time necessary. The time. So see, these problems give you multiple steps that you have to go through in order to get to the final answer. Okay. So we're almost there. You're almost there. And remember, you're still using the second integrated rate law. All right. So that's 1 over A equals 1 over your natural. I keep saying natural because that's the other one. That's the other one. So you're 1 over your initial concentration, okay, plus KT. You've seen that one before. All right. So all you have to do now, this right here is your A, okay, that you're going to use for this problem. So you're going to say 1 over 0.00025 molarity. That's equal to 1 over 0.250. And again, that number came from up above, okay? Plus your rate constant, remember that 84 number? That was up above as well. And that was per molarity per seconds. And then times T. And that's what we're looking for. We're looking for the T. Your time. It says how much time necessary. And so now all you have to do, okay, is go ahead and do the math, get T by itself, and now you are coming on home. All right. So let's go ahead and do this from this part right here. 1 divided by 0.00025, and that's 4,000 equals, and I'm leaving the units off, guys, because the M's are going to cancel anyway, and you're left with seconds as your answer. And then 1 divided by 0.250 gives you 4. Plus 84 times T. Now, this looks like math you're familiar with. 4,000 equals 4 plus 84 times T. This is why they tell you you need at least, college algebra to do this type of math. When they say chemistry is math, this is what we're saying. 4,000 minus 4 is 3996. That's equal to 84 times T. You're going to divide 84 by both sides, and we're going to get our T. So your T is going to be equal to 3996 divided by 84, and that gives you 47.6 seconds. 47.6 seconds. Okay. Any questions from anybody? And this is one of those test questions. You see how long it took me to do it, right? Well, imagine how long it would take you to do it. And this was just one question. And it still has other parts. Okay, we still have letter F and letter G, but I wanted you all to at least see that a question like this could be worth 20 points. You've got 1, 2, 3, 4, 5, 6, 7 parts to this. This could be like worth, 2 points. And then these others could be, worth 5 points. Okay. Now, letter E says, assume the above reaction is elementary, write the rate law. Okay. In case you forgot the reaction, let me go ahead. I'm going to copy it down here so we don't have to keep scrolling up and down. Okay. So let me go ahead and take this here. Okay. Here's your reaction right here. 2NO2 yields N2O4. They told you to assume that this is an elementary reaction, write the rate law. Yes, they're on my YouTube channel, and I'm going to upload this one as well. For this one, because you're only dealing with this one reactant right here, okay? For that one, your rate is going to equal to KNO2 to the second. Does anybody know why I put the 2 up here? Does anybody know why I got the 2 there? It's really easy. And it really depends on when you came in here. The 2 comes from what they told you before. To make it second order, yes. And also, what did they tell you in the problem? When you were dealing with your values here, the units, yep, the units told you the story. Yes, the units told you the story in this process. And if you look at the rate constant, that was the main buzzword right there. If you knew what the rate constant's units were, that told you everything you needed to do for every other question here. They told you per molarity per second. Per molarity per second tells you second order. So that's why I put the 2 there for second order. Okay. And then they want you to determine the initial rate of the reaction. All right, we can do that. Right here, you're going to say, all right, we're going to use our formula. Since they're asking you to find the rate, all you're going to do is take that 84 that they gave you from above per molarity per seconds, right? And then you're going to multiply that times the concentration that they gave you, 0.250. They gave that to you earlier. And that was in molarity, but you have to square that. Okay. Right here. Angel, what you mean you quitting school? Yes, if you lost order, you lost everything. Yes. So, yes. And then this is why you got to know what those orders also represent in terms of the reaction. Yes. Yes, yes, yes. So I'm going to go ahead and take the square of that number. Okay, I'm going to square 0.250 and I get 0.0625 m squared, okay, times 84 per molarity per second. Now, also keep this in mind too. You see how you have, let me write this right here, 1 over m in seconds right there, right? And then up top, you have a molarity squared. Watch this. Because I have an m on the bottom, I'm going to cross that one out with 1 on the top. And that's why the unit here will be molarity per seconds. That S still stays on the bottom. When I multiply these two numbers right here, my final answer becomes 5.25 molarity per seconds. Okay. All right. Now, that's a lot to digest. That is a lot to digest. And I also will like to say this, okay? When you guys are given problems of this nature, spread it out. You know, write everything that you know. And you have to organize your notes, okay? You have to organize your notes so that you know that this problem matches with that set of notes that your professor told you. And then go back and rework them again. Like, y'all, if I were you, I would rework this problem again. Just so you could have it and to know that if you see this on your test, oh, and you know what? Something else. Go back and rework it as if I told you that this was first order. Rework it as if I told you this was zero order. Why do I say that? Because you always want to have more than one way to do it. So go back up here. I'm not going to do it right now, but I'm just telling you what you could do. You could actually change these units to where it represents a first order problem. Change these units to where it represents a zero order problem. That way you are able to see many different scenarios in using all of these formulas that we've talked about. Okay? So, guys, with that being said, I've got to go.